Thank you, Daryl, for the introduction. So as Daryl announced, we are going to talk about diagnosing compilation problems using the Jit Verbose log. I move to the next slide? Okay, here we go. So most of the people in the audience, I'm guessing, are already familiar with Jit logs, but I would like to stress out that the Jit actually has three major types of logs. So we have Jit Verbose Logs, we have Jit Compilation Logs, and Jit Runtime Logs. Jit Verbose Logs mainly show the high-level information about compilation activity, and they are very good at understanding what the JVM is doing from the Jit compilation point of view. And I typically use them as my first approach for diagnosing performance problems, but they can also be used as an aid for functional issues through the so-called limit files. And I'll describe limit files later in this presentation. So a typical invocation would be something like this, xjit verbose, then you specify what you want to monitor and then where to put that information. In contrast, Jit compilation logs show in-depth decisions of the IL generator, the optimizer, and the code generator. They show why the code looks the way it looks, and this can be crucial for debugging functional issues. Of course, we may have a performance issue due to suboptimal code, and in this case, Jit compilation logs can be used for tracking performance problems. I put on the slide a link to some documentation on Jit compilation logs, which you may find quite useful. A typical invocation for generating Jit compilation log is something like this, xjit. Then in curly brackets, you specify the name of the method you want to monitor, and then the level of tracing, and then where to put that information. As you can see, we limit ourselves here to just one method, or it could be a small set of methods, because these logs tend to be very large. And finally, we have the Jit runtime logs, and we use them mostly for showing AOT relocations. You can change the level of information or the amount of information that is generated using this AOTRT debug level. It should be mentioned here that there is a single verbose log per JVM, but there could be several Jit compilation logs, and we may have several Jit runtime logs in order to avoid interferences between different compilation threads writing to the same file. So each compilation thread will write to a separate file. In this presentation, we are going to focus solely on the Jit verbose log. That is the first category, and I'm going to ignore the remaining two. Now, the agenda. Because there is so much to talk about, as Daryl mentioned previously, this presentation is going to be split into two parts. Today, I'm going to explain how to use verbose logs, and I'm going to teach you how to decipher or interpret the logs. And in the second part of the presentation, which is taking place 2 weeks from now, I'm going to show a few points about tracking performance issues with verbose logs, and I'm going to conclude with just one slide with advice for developers. By the way, I would like to say that because the information is quite dense, maybe the audience can interrupt me after each slide with questions or additional information rather than waiting for all the questions to bundle up at the end. It will give you better context for that question. And I'm going to pause slightly at the end of each slide. Okay, so verbose logs can contain a lot of information about many subsystems in the Jit. For instance, they can show environment information like the GC version, the Jit version, the VM version. It can show the Jit options in play. It will also show information about the processor being used, about the memory available to JVM. It can show many things about compilation activity, like compilation starts, ends, failures, recompilations, compilation time, compilation queue size, and the list goes on and on. It also can show various runtime information. For instance, information about the Jit phase or state, or activity for Jit hooks, runtime assumptions, class loading, unloading, code cache allocations, and again, the list is very, very large. here I'm going to focus, or in this presentation, I'm going to focus only on on a small subset of all this information because it's just too much to cover. And this is going to be a biased view. So I'm going to focus only on the information that I typically used in my performance investigations. Any questions so far? Okay, if not, I'm going to move. So to use vlogs, you need to specify what you want to track and where to put that information. And the simplest form of invocation is xjit verbose, and then vlog and specifying the file name where the information goes. So this type of invocation prints options, prints configuration of the JVM, and the finished compilations, either successful or failed. Typically, this form of invocation is used for generating limit files. And a short parenthesis here for newcomers that don't know what limit files are. So these are files that specify which methods are allowed to be compiled, and use them when you try to limit a functional problem to a smaller and smaller method set. Hopefully you can reproduce the problem with just one method being compiled, and then you proceed to generate a Jit compilation log for that method, detailing the native code being produced. For more advanced uses, you can specify what the verbose logging facility needs to track, or the so-called vlog category. And I'm showing here a few examples. So you specify verbose equal, and then in curly brackets, the category that needs to be tracked. And then, of course, where that information goes, the vlog name. If you want to observe more than one category, you can list them like this: verbose equal category 1, comma, verbose equal category 2, and so on. There is another way of specifying several categories, and it's showing it here in the third invocation, with verbose equal, and then in curly brackets, you put all the categories that are separated by these or signs. Now, if you use this type of verbose options, then you may need to do some escaping. And because of that, I typically prefer the second type of specifying the options. There is a fourth way of specifying the categories, and that is using regular expressions. We use simple regular expressions, and in all my use cases, I only seen use the star, and I have here an example. So we can say compile star, and then any category that starts with compile will be monitored. Of course, you can say verbose equal and then star, and that means you are going to monitor absolutely everything, but the vlog starts to become quite large if you do that. If you don't specify a vlog file name, then the output goes to standard error. This may be convenient sometimes, especially if you work with containers and Kubernetes, let's say, and you already track the standard error from those containers. But in most cases, this is a nuisance because information from the application itself, because the application can write to standard error as well. So the information from the application or from other JVM subsystems like GC, if you don't specify a GC log, then the information goes to standard error. So the vlog, not the vlog, but the standard error now will contain information from different modules, and it's hard to track what generated what. And especially if you use a parsing tool to parse that information, it's going to be very hard to separate the information coming from different subsystems. So most of the time, I output that vlog information to a file. Now, if you specify a file like this, let's say vlog equal to vlog.txt, on the file system, you'll see something like this. So there is a suffix being appended to the name that you specify. And that suffix is composed of the date when that vlog was produced, the time, and the PID of the JVM that produced that vlog information. This is quite useful because let's say you have an application that under the cover may use different or several JVMs, then you can see how many JVMs were invoked. And also you keep the vlog information from these JVMs segregated. So each JVM will produce its own vlog. If you don't like that, you can specify an option, xjit disable suffix logs. This is convenient if, let's say that you have to deal with just one JVM. You may start that JVM over and over, and you don't want to look on the file system to see what's the name of the vlog that has been generated. You just have to look for this vlog.txt if you provide this disable suffix logs. So a convenience option, if you will. Verbose options can be specified either under the xjit heading or under the xAOT heading. So it doesn't matter where you put it. For those of you that don't know, the Jit compiler can perform two types of compilations. So we have, let's say, normal just-in-time compilations and AOT compilations. So AOT stands for ahead of time. So these are compilations that are produced in one JVM invocation, stored into the so-called shared class cache, and loaded from the shared class cache very quickly in subsequent invocations of the JVM. Jit compilations are controlled by options under the xjit heading, while AOT compilations are controlled by options provided under the xAOT heading. Now, if you specify a vlog name under both headings, then the vlog name that is going to be used is taken from the xjit heading. That's because vlog name is a static field in the options structure. And first, AOT options are processed, and then we process xjit options, and it's going to override whatever you put under xAOT. However, if you specify different verbose categories under both xjit and xAOT, then these categories are additive. So whatever is specified under xAOT is going to be added to whatever is specified under xjit. Just to keep things simple, I always prefer to specify all the verbose options either under xjit or either under xAOT. Any questions so far?
Mary, sorry, just I wanted to clarify what you said on that last point. Even though specific xjit or xAOT options are separate from, I guess, directing to regular compiles with xjit and AOT compiles for xAOT, the verbose options would capture both AOT compiles and regular JIT compiles if you specify it in either.
Yes, that's correct. So they're static, so they don't refer to a particular compilation. They refer to compilations as a whole.
I see. Okay, thanks.
Yeah. So even though you may have AOT compilations, if you specify verbose for xjit, it will show AOT compilations as well. Those will not be ignored.
Right. Thank you.
Okay. So this slide shows a short list of vlog categories that I use the most. So this is a biased view, if you want. For instance, we see here compile start, which will give information about compilation starts. We have compilation end. This, of course, as the name suggests, will give information about compilation completions. We have an interesting one, compile performance. This is a convenience category because under the covers, it enables other categories like a compile start and compile end, but also other pieces of information that are typically used in performance investigations. And for the vast majority of the cases, this is the sole category that I'm using. Of course, from time to time, I may add different ones, but by far, this is the most one, the one that I use the most. We also have compile request, which will show you when an application thread is putting a request into the compilation queue. Compilation dispatch will show you more detailed information about compilation thread activity. Compilation threads will show you when compilation threads are suspended or activated based on the load. It will also show you the CPU utilization taken by different compilation threads. Compilation failures will show you when methods fail, but also show you if the method will print a different message if the method remains interpreted after a compilation attempt. And we also have sampling and inlining. I'm going to talk about this later in the presentation. Jit server is an interesting category. I use it a lot just because I work a lot on the Jit server. So as the name suggests, this will give you information about the Jit server activity, and not just the Jit server itself. So if there is a JVM attaching to the client, then this will give you information at the client as well. Some people prefer to use compile star, and therefore that expression will include anything between compile start and compilation threads from this slide. So it will include several useful categories. Now, this slide is an exhaustive list of all the categories that exist presently in the JVM. They are not ordered alphabetically. Unfortunately, there isn't documentation on any of these, but then again, we don't provide much documentation, if at all, on Jit options. For some of them, the name could be quite revealing on what it does. Let's say code cache, you can guess that this is going to give you some information about code cache allocations, whereas other categories like link, even I don't know what it does. So you have to follow the code to understand what a particular category is going to track. Any question? If not, yeah, this is the second part, actually the second part of the first part. So now let's see how to read that vlog information. And again, I'm going to focus only on the vlog categories that I use the most, and that is compiled performance, sampling, and inlining. So at the beginning of the vlog, you will see information about the environment. So you'll see the Jit level, the JVM or the VM level, and the GC level. You'll see information about the processors that are used to run this JVM, their type, and how many. You'll see the options in play, the Jit options, I should say. We do not print the JVM options, but we do print the Jit options. You may also see a line like this one here in, I'll say that's a brown color, and hopefully you will not see it. Why? If you run an application for which startup or ramp up is important, then you probably want to use AOT, ahead of time compilation. Now, if you are looking at the vlog and you don't see any AOT loads, you should search for such a line showing that the AOT header validation failed, and that's your reason why you don't see any AOT loads. Why can the header validation fail? Well, maybe okay, let me backtrack a little bit. So when you run with AOT, you can distinguish between the so-called cold runs. Those are the runs that populate the shared class cache with the AOT code, and the warm runs. Those are the ones that take advantage of the information of the AOT methods that are already stored into the shared class cache. Now, it may be that the environment that was used to populate the shared class cache is different than the environment that is using the shared class cache, and that difference generates this incompatibility. And let me give you a few examples. The one that is shown here is due to a processor incompatible. So if you are generating the AOT code, that is the cold run, with a new processor with many up-to-date features, and then you are trying to run this JVM, so you have the warm run on a processor that is very old, that processor may not understand some of the instructions that were used in the AOT bodies generated on the newer processor. And in that case, we are not allowed to load any AOT bodies. This probably is not going to be seen in practice that much, but there is another case that you have to keep in mind. That's when the so-called compressed ref shift amount is different. So you may be running the cold run, you may be executing the cold run with a small amount of heap. In that case, the compressed ref shift could be 0, let's say, because you are running a very small amount of heap. But in a second run, the warm run, you may provide a large heap. And in that case, the compressed ref shift is large. It could be 3, it could be 4, or you may not even use compressed references at all. So in that case, again, you cannot use the AOT code that has been generated because there is a discrepancy between the cold run and the warm run. So to make a long story short, if you think you should have AOT loads in your run, but you don't see any, look for such a line showing that the header validation failed, and then you'll find the reason for why that validation failed. Other types of information for the environment, it will show start time of the JVM. This is useful if you have several JVMs and you want to align the vlogs from different JVMs. Or maybe let's say that the user has told you that at such time the performance was very low, and then you have to go into the vlog and see what happened from the compilation point of view during that time. So the start time for the JVM becomes very useful in that case. CPU entitlement and physical memory. Again, this information may become important in some cases, and I'm going to explain this why in the second part of my presentation. Another piece of important information is statistics about the share class cache that this JVM attaches to. And you'll see here how much free space you have in the share class cache, how many ROM classes and AOT methods. So this may tell you whether or not this share class cache may be too small and you could benefit from a larger share class cache, or maybe if you have too few methods, AOT methods. Or it also gives you indication whether this was a cold run or a warm run, just looking at the number of AOT methods. Any questions?
Is there an easier way to get the type of insights that you just shared in terms of analyzing this data? Because obviously you have a lot of information, right? So like, whether
yes.
it's a cold run or warm run, whether it's full and what someone should do about it.
I do have some parsing scripts, even though I'm not going to parse this information directly, but I'm providing statistics on, let's say, the number of AOT loads and all the compilations that are taking place. So if you're looking at those statistics and you see no AOT load, then you start to scratch your head, why is that? And then you should be looking for this type of information.
I'm even thinking more at a higher level, right? Whether like a Java developer using OpenJ9 could have a way of getting essentially your configuration is suboptimal. This is why, and these are the steps that you should take.
Yeah, we don't have those kind of tools. So in a sense, a while ago, we started to put that kind of logic into the health center. Unfortunately, we know what the state of health center is these days. So we had even some changes that never made it into the public version of health center. So yeah, we started to put that smart into health center, but
I see.
yeah,
Okay, this is a separate topic anyways. I don't want to distract you.
Yeah. Okay. Now let's look at the anatomy of a compilation start line. And I put here all the information, but we'll go step by step. A compilation start, of course, will be printed when the compilation starts. Such a line starts with a blank space, which you cannot see here, but it also includes this word compiling. So that's your sign that you have a compilation start. So now let's go and examine each part. So in blue, you see the optimization level at which this compilation is going to be performed. Most of you know that we have different optimization levels: cold, warm, hot, very hot, scorching. There is also something called no opt, where there is no optimization being provided, but that is mainly used for diagnostics, and during normal runs is going to be seen in very, very limited cases when the compilation fails at cold and we have to resort to a no compilation, hoping that the compilation will pass. But if you have a compilation that fails at cold because it's too complex, then I think we have a bigger problem there. The optimization level is actually just warm, but this may include other information like the type of the compilation. In this case, we are performing an AOT compilation, so that's why you see AOT warm. If it was a JIT compilation, you'll not see JIT warm, it's just warm. So that's how we distinguish between the two. You could also see a word like profiling. So if this compilation is going to include profiling trees, just to give you a big topic, a small refresher. Sometimes the JIT may want to collect profiling information so that it can better optimize the code in a future method body. And in that case, the optimizer is going to insert profiling trees in this method body that is going to be generated. And if that's the case, you'll see the word profiling and maybe hot or profiling very hot here. Okay, moving on. So in orange, we have the method name, that's self-explanatory. In green, we have the method type. Most of the time, you'll see ordinary methods, but you can see other types of methods as well. And I put here some of them. This is not an exhaustive list. You can see method in progress. This is also called the DLT, or dynamic loop transfer. You may see method handle thunk, other thunks, archetype specimen, and again, the list goes on and on. Most of the time, this is an ordinary method. Okay, in purple, we have the J9 method pointer. This may be useful if you have an application that uses different class loaders to load the same class. And in that case, you may have the same name appearing twice, but from the JVM point of view, those methods are different. They'll have a different J9 method pointer. So this is useful in those situations to distinguish between the methods that are actually distinct, even though they have the same name. In baby blue, we have the time when the compilation started. This is expressed in milliseconds since the start of the JVM. And the resolution for this is roughly 10 milliseconds. So not a great resolution, but for most common purposes, it suffices. In red, we have the compilation thread ID that will perform the compilation. In navy blue, we have the Jit Scratch Memory limit. So in order for the JIT to function, it needs to allocate memory, and that is called Jit Scratch Memory. Of course, we don't want the JIT to use the entire memory on the machine. So we place some limit on how much memory a compilation can use. And typically, that limit is 256 megabytes as shown here. However, there are cases where this limit is different from 256. For instance, JSR292 methods are allowed to use up to 1.5 gigabyte of memory. Another case is where you use Xtune virtualized. So under Xtune virtualized mode, the compilations are limited to 16 megabyte of memory. And there are also some rare cases where the free physical memory is very low, and in that case, we adjust the memory limit to match that. We cannot use more memory than we have on the machine. And finally, in gray, we show the free physical memory available to the JVM. So if this is running natively, then that is probably the same as the memory for the entire machine. However, if you are running in a container and you already place a memory limit on that container, this value will reflect that limit as well. So it's the amount of free physical memory that is available to the JVM itself, not to all the processes on the machine. I guess that completes the compilation start line. It's time to stop for questions. Okay, let's move then to compilation end line. The compilation end lines are printed, of course, when the compilations are done, and they always start with plus if the compilation is successful. Next is the optimization level. We've already discussed that. Maybe here I should mention that if you have an AOT load, then this will show AOT load. It's not going to show AOT load warm or something like that. So you'll not necessarily be able to tell what optimization level for that AOT body is, but it will show as an AOT load. Then we have the method name, again, very simple. Next one is the native body memory range. It always starts with an @ sign, and then it has the memory range where the code for this method resides in memory, in the code cache, to be more precise. And the first pointer is the start PC, or the interpreter entry point for that method. Then we have the type of the method. We already talked about that. Next one is the one character that's indicating the reason for recompilation. Now, in this case, we have a first-time compilation. So this is an interpreted method that for the first time is compiled. This is not a recompilation. That's why it shows as a dash. But if this was a recompilation, we may have a letter here indicating why that recompilation took place. For instance, if this was due to an invalidation, you may have an I, and I put here a few common reasons for recompilations. If you see a G, it could be due to the guarded counting recompilation mechanism. Let me backtrack a little bit. So what is this guarded counting recompilation? So this is a mechanism where we place a counter or we place code at the beginning of a method, of a JIT method, where every time the method is invoked, that counter will be decremented by 1. And if that counter reaches 0, we trigger a recompilation, and then you'll see a G in there for the reason for recompilation. This is called guarded because counting is not enabled all the time. We want, for instance, to disable counting during the startup of applications because we don't want to affect the startup time. Yeah, I guess that suffices. You may also see a T there, which stands for threshold based. So here you compare the number of samples this method got against a particular threshold in order to decide whether to upgrade this method to hot and scorching. And that's why you can see a T. The T is quite common for hot and scorching compilations. You may see a Z. So each compiled body has a counter that is decremented when that body receives a sample. Again, if that counter reaches 0, we trigger a recompilation, and in that case, you may see a Z in there. J stands for J profiling. So you can have JITted methods that are collecting profiling information. When the body determines that it collected enough profiling information and it's time to upgrade this method in order to take advantage of that profiling information, a recompilation is triggered and the reason is going to be noted with a J. Called upgrade. The default optimization level is warm. However, in order to improve the startup time of applications, the JIT may decide to degrade optimization level from warm to cold. However, if a method receives a method that was compiled at cold receives enough samples, then it can be upgraded back to warm. And in that case, you'll see a C. A stands for forced AOT upgrade. Code that is AOT, so there's AOT bodies, the quality of those bodies is not matching the code quality for regular JIT compilations, and we try to upgrade them again through the sampling mechanism. If such an upgrade happens, then we may store a hint into the shared class cache such that in the next invocation, when that AOT load is happening, we are not going to wait for new samples in order to upgrade this AOT body. We will see that hint into the shared class cache and immediately schedule an upgrade compilation for this AOT body. And in that case, you'll see an A in there. And S stands for secondary queue. I'm not sure how many of you are aware. We have two compilation queues in there. So one is the main queue, and then there is a secondary queue, which is processed only when there is nothing into the main queue and when there is the JVM has still some idle CPU that it can use. Because this was a big topic, I'm going to stop here for questions.
I just want to confirm what invalidation is referring to there. Is that like a pre-existence?
Exactly. Yeah. So there is an optimization.
Hierarchy.
Yeah. There's an optimization called pre-existence, and that may render the running body as invalid. We cannot allow the application to run that invalid body. So we generate a synchronous compilation and that synchronous compilation will have a 9 there because recompilation is due to invalidation.
Okay, thanks.
Is there a
sorry.
reason you decided to put a method into the secondary queue to begin with?
Yes, sometimes we want to accelerate ramp up, and we may put in there methods, interpreted methods that haven't actually reached their invocation count. So their time hasn't come yet. But if there is nothing else to be done, if the JVM still has some idle CPU, there is no other compilation going on, we say, let me schedule some of these compilations ahead of time. Of course, I'm going to sacrifice there some interval profiling information, but from the ramp up point of view, maybe that's a good decision.
Okay.
So these are, in a sense, speculative compilations.
Okay.
Okay, any other question? I thought somebody else wanted to ask something.
Yeah, that was me. Does invalidation, this capital I here, also apply in case the body was invalidated because of speculative optimizations relying on OSR?
I do not know that, but what I know is that invalidations are always synchronous compilation. So if OSR triggers a synchronous compilation, then probably the answer is yes. That's the OSR can trigger an invalidation. So I do not know that much on OSR.
Okay.
To answer your question, so my experience is
That's
just
all right.
pre-existence. Okay, so
Thanks anyway.
yeah, no problem. Moving on, queue size represents the compilation queue size, and queue size I is the number of interpreted methods waiting in the queue. And if you do the subtraction queue size minus queue size I, you'll find the number of recompilations that are waiting into the compilation queue. QW is compilation weight, compilation queue weight, and this is needed because, of course, compilations are not equal. So you can distinguish between 100 AOT loads waiting into the queue versus 10 scorching compilations waiting into the queue. So those 10 scorching compilations are probably going to require much more time. And therefore, each compilation also receives weight, if you want. This is just an estimation. Of course, we don't know how much time or effort the Jit compiler is going to spend on a particular compilation before it starts. So it's an estimation, but it works pretty well. And we use this queue weight to determine whether or not we need additional compilation threads to solve the compilation queue. So if that compilation queue grows too much, then we launch another compilation thread. If it drops under certain levels, we may suspend compilation threads. J9 method is the method pointer. We explained that. Bytecode size is the method size in bytecodes. Then we have some attribute for this compilation. In this case, it says that this method has GCR code in it. I put here examples for other attributes. JNI is natives, OSR, on-stack replacement. JProf, it means that the body has profiling code in it. Remote, it means that this method has been sent to a Jit server, so therefore remotely for compilation. And sync, it means that this compilation is synchronous. Most of the compilations are actually asynchronous, and in that case, you will not see an async. Only if the compilation is synchronous, you'll see a sync in there. Sync means that the application thread has to wait for the compilation to finish before it can proceed. And asynchronous means application threads and compilation threads can go in parallel. Time is the elapsed time needed to compile this method. It is expressed in microseconds. Then we have the Jit Scratch Memory used to compile this method. And there are two numbers. The second one, the system, it's the number, or represents the number of, actually not the number of segments, the number of, the total amount of segments that have been allocated for this compilation. Because the Jit allocates the Scratch memory in segments, and the size of one segment is 16 megabyte. In this case, it finished this compilation by allocating just one segment of 16 megabyte, but it only used 2 megabyte out of that segment. Compilation thread ID that performed the compilation, that's self-explanatory. CPU load, so this is the CPU utilization on the machine as a whole. In this case, it says that the machine uses 3.4 cores. And if you think on the machine as a whole, it uses 42% of the entire machine. So this can go up to 100. This machine had 8 virtual cores available. And finally, we have the JVM CPU, which is the CPU utilized by the JVM itself. If you subtract the CPU load, if you subtract JVM CPU from the CPU load, then you find that 0.4 of a core was used by other processes running on the system. Okay, I think this finishes the compilation end line, so it's time for another pause. Any questions?
I have a question.
Yep.
Does this segment get used by other compilations, or is it just attached to this specific one?
No, we don't share Scratch segments between compilations. So this segment will be used by this compilation alone, and another compilation will allocate its own Scratch segment.
So the 14 megabytes are wasted or used in this?
16 here. I'm not sure about the 14.
So only two were used, right? 2 megabytes were used out of the 16?
Yes. Yeah, so we allocate an entire segment of 16 megabyte, but we only use the 2 megabyte out of that.
So 14 will always stay unused?
Well, yes, it will stay unused until the end of the compilation. At the end of the compilation, we actually free those segments. So it's not going to be hanging on those segments forever.
Got it. Thank you.
Okay, so now let's look at the compilation failure line. I put here the entire structure of the compilation failure because it's going to look very similar to a compilation end. In essence, a compilation failure, it is a compilation end, but with a different outcome. The compilation attempt failed. There is one big difference though. A compilation failure starts with an exclamation mark. So instead of a plus, you'll see this exclamation mark. Then we have all these fields that I already talked about. Another important difference is that a compilation failure will include a reason for failure. In this case, it's compilation interrupted. There are many, many reasons for failure. It's a big list. I put here down a few of the most common reasons for failure. Compilation interrupted basically tells you that GC tried to unload classes during a compilation, and in that case, we need to abort this compilation and retry it. Compilation excessive complexity may happen because the optimizer discovered that the method has too many loops, too many nodes, too many blocks, and so on. And we will abort this compilation. If this is a first-time compilation, we will retry it at a lower optimization level. If this is a recompilation, then we will not retry it. We will just use the body that already exists. Compilation CH table commit failure. You may also see this from time to time. So some of the optimizations are speculative in the sense that they look at the status of the class hierarchy and they base the optimization on the current status that is seen. We may record some assumptions about that state. And at the end of the compilation, we do what is called the CH table commit. We examine that our assumptions are still true. If those assumptions are invalid, we may abort this compilation and try it again, hoping that the next time around the class hierarchy will not change such that it will lead to a failure. Compilation heap limit exceeded may happen if the JIT tries to use more scratch memory than it is allowed to use. Compilation enforce profiling. This can happen if the optimizer decides that it may do a better job if it had some profiling information. Therefore, it may internally switch to profiling. So from a non-profiling information, it wants to turn into a profiling compilation, but that is not always safe to do. And if it decides it's not safe, then it will kill this compilation, abort this compilation, and try it again and starting as a profiling information from the get-go. And the last three are compilation failures due to various cases with AOT loads. You would see those quite frequently. Yeah, do I have anything else in here? Any question before moving on? Okay, if not, I'm going to the JIT state. So the verbose log can also help you understand the different phases of the application. And the JIT detection mechanism of the phases is not always accurate, but for the common scenarios, it comes pretty close. The JIT state is important because the JIT has different heuristics for different phases. So knowing the phase may let you understand why the JIT took a particular decision. And currently, the JIT track the following phases: idle, startup, ramp up, steady state, and deep steady state. And by the way, I'm using the word phase and state interchangeably. The lines in the vlog are prefixed with hashtag JIT state, so it's very easy to grab for them. How do you generate this information? Well, there are two ways. You can specify compile performance as shown here, and this will print only the state changes, or you can go for verbose equal JIT state, and this will print a line with the state every half a second. I typically use the first type of invocation. It's more like a summary, whereas the second one is just too much, and I typically use it only when I want to debug the JIT detection state. Otherwise, this suffices. So let's look at this example that I have here. So one such line with JIT state will include the time when the JIT state change happened. In this case, in this case is 26.7 seconds. As I mentioned previously, this is in milliseconds. And it shows that here the JIT transition from startup to idle. And after that, there are a bunch of statistics that may give you some information about why that transition took place. It shows you the number of compiled samples, interpreter samples, compiled methods, recompilations, queue size. We have the JVM CPU. And we also have something called CLP, or class load phase. So this is a mechanism that measures the rate at which class loading takes place in the JVM. Why is that important? Because if a JVM is loading many classes per second, we think that that is either because the JVM just started, or there is a phase change into the application. And if there is a phase change, we want to drop the optimization level from warm to cold to accelerate that. So a class load phase is typically associated either with ramp up or with startup. We want to accelerate both. And I have an example here where we declare that the class load phase was on. You can see other signs that there was a phase change here. All of a sudden, the JVM CPU jumped. There are many interpreter samples. Also, this is a sign that new methods were injected into the system, or at least those methods started to be executed. Any questions on this one? Okay, moving on. So this slide shows you how to decode the sampling information that can be available or written to the vlog. So the JIT has a sampling mechanism whose main purpose is to determine the hardness of the methods. If you want to understand why a particular method has been promoted to a higher optimization level or not, you may need to generate a sampling vlog that will show you the decisions taken by the sampler. All those lines start with hashtag sample. So again, it's very easy to log for them. And you have two types of lines. You may have samples in interpreted bodies or samples in compiled bodies. Both of them start with a sample count, which is just a counter that increments when a new sample has been received. So let's look at the interpreted sample. So you have the word interpreted, then you have the name of the method that receives the sample, and then in light blue is shown the action that is taken. In this case, the action is to reduce the invocation count from 449 to 28. What is this count? So every interpreted method has an invocation count. It starts at a predetermined value, and every time the method is invoked, that invocation count is decremented by 1. When the count reaches 0, the method is compiled. Now, some methods are more meaty, have more meat in them than others. You can compare a getter that is a very simple method versus a matrix multiplication method. So if you spend more time in an invocation for a method, you want to accelerate the compilation of that method. And we do this through the sampling mechanism. If an interpreted method receives a sample, we more or less abruptly decrement the invocation count to accelerate the compilation of that method. And the acceleration is done by dividing the invocation count that you see at that moment by 16. And that 16 can be configured, of course, with an option. Now let's look at a sample for a compiled method. So here you have the word compiled, then you have the name of the method that receives the sample, have the start PC of the method receiving the sample. In purple, we have the offset where the sample falls. Count is the value of the sampling counter. When a method gets compiled, it gets this sampling counter. It starts at 500 by default. And every time this method receives a new sample, this counter is decremented. If the counter ever reaches 0, this method is going to be recompiled. At what level? It's indicated by NCL, next compilation level. In this case, it's a 3, which is hot. And I put here how to decode those numbers. So 0 is not, 3 is hot, 4 very hot, and so on. Other pieces of information that you may find on this slide are here in brown. So we have the window of sampling. We don't want to take a recompilation decision every time this method gets a sample. We wait for 30 samples to take a hot recompilation decision and 60 samples for a scorching recompilation decision. We wait longer for scorching recompilations because we have to make sure we didn't catch just a blip into this method becoming all of a sudden more active. So we have to be more sure because we also tend to spend more time in compiling at scorching. So these are the decision windows. We also have these samples. These are the samples that every single method receives. Again, two numbers because one refers to scorching and the other one refers to hot compilations, hot recompilation decisions. And this current sample interval count is the number of samples this method got in the current window. This number will start from 0, it will go 1, 2, 3, up to 30, actually up to 60, and then it wraps around. It starts again from 0. So we'll, as I said previously, we will not take a decision until this value reaches at least 30. So for this particular example, the decision is not to recompile because the sample interval is not done. We have to wait until this number, the number of samples, reaches 30. Let me cover the next slide as well, and then I'll pause for questions. So this slide shows the history of a method. It's the same method when it receives a sample. So not all samples are shown, only the more important ones. The first line is actually the previous example that you've seen on the slide just before this one. So I'm not going to discuss it further. The decision was not to recompile because the sample interval was not done. We want the number of samples this method receives to reach 30. The second line, well, now the current sample interval has reached 30, so it's time to take a decision. We have, through the options, we can control some recompilation thresholds. Those thresholds are going to be scaled based on the size of the method. We want smaller methods to be more aggressively recompiled at hot and scorching, while bigger methods less aggressively, because we spend more time in bigger methods. So those thresholds are going to be scaled based on size. In this case, the size scaling is 0.8. So this method is basically smaller than what we consider to be the average method. So after scaling, we find these scale thresholds, 0 and 772. Again, we have two because the first one refers to scorching, the second one refers to hot. We are going to compare these thresholds to the samples that all the methods in the system got. And they are the same because the sample count interval is 30. They will start to differ when this goes beyond 30. So the comparison is between this number 801 and 0, and because 801 is greater, we say no, we are not going to recompile at scorching. Actually, this is on purpose 0 because we never want to recompile at scorching if our sample interval has not reached 60. This is the window here. For hot recompilation, again, we compare this 801, all the samples that everybody method got, to 762. It's still greater. So we say, no, we don't recompile at hot. The decision is to not recompile. And we also reset the count to 500. So this count, which is, I told you, starts at 500. This method received 30 samples, so this count was decremented by 30. But now we found that this method is relatively cold. We put back 30, so this count will become 500 again, and we start decrementing. So this is why a method is very unlikely to be recompiled through this count becoming 0. It's more likely to be recompiled by the comparison between the samples that all the methods got and these scaled thresholds. If you are wondering how did we come to this CPU 3.7%, this is done by dividing the number of samples this method got, which is 30, we know that, to the number of samples that everybody else got, and this is 801. That will give you 3.7%. Now let's look further. So 30 more samples fall, and the current sample interval count has wrapped around, has reached 60, and it becomes 0 because it wraps around. Again, we compute our scale thresholds, and we find 366 and 762. To decide whether or not we want to recompile this method, we compare again this number of samples that everybody else got during the interval to 366. It's bigger, and say, no, we don't recompile at scorching. How about hot? We compare 434 to 762. It's smaller. Then yes, we are going to recompile this method at hot. So the decision is to recompile at level 3. We've seen previously level 3 stands for hot. Again, how do you find this 4.8 CPU? Well, you divide 60, not 0. So this method has received 60 samples by this 1235, and that will give you 4.8%. Now, we decided to recompile the method. The method can still receive samples, but the samples are going to be ignored because this method is undergoing recompilation. And then the compilation finishes. Unfortunately, the compilation has failed. Why has failed? Because the compilation heap limit has been exceeded. So the compilation tried to use more scratch space, more scratch memory than it was allowed to. Now, what happens afterward? We are not going to retry. We don't want to retry this compilation because it's likely that if we are going to retry it, it's going to fail in the same way. Therefore, any additional sample that falls on the existing body, which is a warm body in this case, is going to be ignored. So we say that this method has failed a recompilation attempt. Don't do anything further. In the future, we may change this heuristic. So if a method fails because it couldn't be performed at hot, maybe the method was too complex, or maybe it took too much memory, we may want to retry it at hot, but adjust the inlining heuristics to generate a simple body that may succeed. But that's something for the future. So that concludes this slide. So are there any questions? This was, I think, the most difficult slide to talk about. There's a lot of information. So do you have any questions, or it was so complex that no questions? Okay, that's either a good sign or a bad sign. So, okay, I'm going to move on. Finally, the last slide that I'm going to talk is how to decipher inlining output. So inlining is a very important optimization, and sometime we may want to see what has been inlined. Of course, we can derive inlining information from Jit compilation logs, but as I mentioned on my first slide, we typically generate compilation logs for a single method or for a small set of methods because they are very big. So if you want to find information about all the methods that have been compiled, probably using a verbose log with inlining is a better option. The inline information is actually comprised by these 3 lines. So it always starts with hashtag INL. So again, very easy to look for it. But on this slide, I'm also showing the compilation start and the compilation end. So the compilation started. We are compiling string.length. Just before the compilation is about to finish, so after the code generator has done its job, we print this inlining information, and it has 3 sections. The first section is just a summary. It shows how many methods were inlined in this method that we compile. So we compile string.length, and in this case, only one method has been inlined. Start PC is the start PC of the method being compiled. So even though this compilation is still in progress, we know the start PC because we are printing this information after the code gen has done its work. There is also a method, a hash for the method name. So you can use this to pair up various information in these lines. So this is the first type of information that you'll find in inlining logs. The second type of information, again, I have only one line, but there could be several lines. So the second type will show you what has been inlined. In this case, we only have one method that has been inlined. The name of the method is string.coder. We have here the callee index. So this is the index for the thing that has been inlined, is the index for this method, string.coder. And we also have the caller index. -1 says this is the topmost method. So this means that we inlined this string coder in the method that is subject to the compilation. We also show the bytecode index in the caller where the call is. And that's all there is. Also the bytecode size of the callee. And the third category of information, it shows you who called what. So this tends to be bigger because not only it shows the methods that have been inlined, but also other methods that could have been inlined, but the inliner didn't due to some heuristics. And then we have this finish, compilation finish line. Again, it's not part of the inlining. So if you want to have, and I suggest it's a good idea to have everything. You may specify compile performance, verbose equal compile performance, and then verbose equal inlining, and you'll have compilation starts, ends, and all this inlining information. Any questions so far? This is the last slide. I can stop here and we can discuss not only about this slide, but everything else that was presented so far. Yes, this is the last question. So any questions on it?
I have one question going back to your the slide that shows the sampling entries.
Okay. This one or previous one?
The
Okay.
I think, well, this one as well. It doesn't matter. Yeah, so this one.
Oh, this one?
Yeah. Oh, sorry, the previous one.
Previous one. Okay, this one.
So the offset there is the offset from start PC.
Yes.
How can I correlate that to the bytecode?
You'd have to have a compilation log, unfortunately.
I would have to have a compilation. Okay.
Yeah.
I think this might be a good poor man's way of getting some basic profiling information and identifying where in the method is hot.
Yeah, and I don't think we can keep that information. I mean, we could keep it with some memory overhead, but I don't know if it's justified or not.
Right.
It also depends on how often are you using the sampling log.
Yep. Okay.
Typically, you would try to identify what method is important, and then maybe you can judge whether or not that method reached the optimization level that you think deserve to reach. And if it didn't, then you can try to generate not only the sampling log detailing what samples has received, but also a compilation log, and then you'll be able to infer this offset refers basically to this bytecode.
Right. Okay, thanks.
So I would imagine that the overhead of the sampling verbose log is quite high with the rate of samples that it would dump in here. Is there any way of controlling that? Like, let's say start reporting samples after 10 seconds and shut it off after 15 seconds, something like that?
Let me remember if there is. I think there is a way to stop the sampling mechanism after a specified number of seconds. I don't remember if you can start it after or start basically if the JVM starts without sampling and then enable it later on. For sure, there is a way of turning sampling off. That was as a measure to actually prove that sampling itself does not affect throughput or performance in general too much. This question has come from time to time, but we never found evidence that sampling may affect performance. Well, if you try to generate a sampling vlog, then yes, because of the constant writing to a file, you may affect performance somewhat. But sampling itself may not generate a lot of performance overhead.
Okay, I was asking specifically about the verbose sampling, like
yes, this can
enabling and disabling the verbose. If there was a way of
no
finer control over that, no. Okay.
No, at least at the present, there is no such option. Sampling as a whole, yes, but just sampling vlog, no. And that's a good idea, though. Yeah, we may want to stop it because after a while, what you'll see in that sampling vlog is sample after sample in methods that we don't want to recompile. Either they have received, they reach scorching, and we don't want to recompile anymore, or methods that will never be upgraded because they are not hot enough. So yes, after a while, the sampling vlog becomes uninteresting.
Okay, thanks.
Do you have any tips or tricks for dealing with having multiple compilation threads putting events into the verbose log?
I'm going to cover that in the second part of the presentation. If you are adding a new verbose line, how to keep that together with logs, basically.
Okay. But is there
Yes.
any information in the log itself that helps with the fact that you've got multiple compiled lines and then and then the compile end line and tracing that information through the log?
Not sure I understand the question. So yes, lines produced by different threads may appear interspersed in the vlog, but one particular line will not be broken by other lines. So you have full form lines appearing through the compilation threads can generate this interspersed information, and then you have to have some logic, the script that parses the log to match the corresponding lines. And I do have, and I'm going to show you next time, I'm having some scripts that does that matching.
Is that inlining output that you showed, is that synchronized across the entire compilation? Like you get one blort of inline
I believe so. I believe so, because it's done in a piece of block. I'm not 100% sure, but I'm 95% sure that it is one block. I mean, everything is synchronized to appear as a standalone block.
Okay, yeah, thanks.
To the next slide, Meros.
Oh, this one.
Yeah, this one. The scale, the threshold. You are talking about, you compare the scale value need to be bigger than the samples.
Yes, in
Trigger,
order to
right?
trigger a recompilation. Yes, that's correct.
I actually thought that it should be the scale, the threshold exceeding certain percentage of the sample, all samples.
Yes, if you do the math, it actually, the scale thresholds are referring to some percentages, but those percentages are scaled based on the size. So if you ignore the scaling based on size, then you'll find some not scaled, but just some thresholds that are part of our optimization, part of the options, and that those numbers reflect those specific CPU utilizations.
Okay, CPU, you're right. Okay. I actually think that if you receive the total samples received by all methods is 400, for example.
Okay, that'll be this number here. Yeah.
If the scale, the threshold, reaching say 300 is 75%, then it should be hot. But in your criteria, actually, you need to receive more than 100% of the 400, right? It's more than 400, then you decided it's going to be hot. Yeah, I think I will ask you in detail offline.
Yeah, because you also have to keep in mind that this method hasn't received one sample, has received 60 samples in this case, or 30 if you're judging based on the hot window.
Okay. It's received 60 sample, but you scale it to 700. Okay, got it.
Yeah.
Okay.
Any other question?
Last call for questions. Okay, if not, thank you, Marius, for informative presentation. I'll stop the recording now, and we'll pick it up again in 2 weeks for the second part. Thank you.
Okay, thank you.